Class, we have seen the analysis of self-bias or emitter bias circuit. Today we shall continue the discussion and we shall discuss also about the stability of the circuit quantitatively and another circuit which can be used for biasing with improved stability. Now, we have seen that a self-bias circuit has a collector resistance and an emitter resistance and a base biasing circuit through resistances R1 and R2. Let us solve a problem for better understanding. Now let us consider a case where the resistance, the collector resistance RC is 5.6 kilo ohms and the emitter resistance is 1 kilo ohm. Then R1 and R2 are 90 kilo ohms and 9 kilo ohms respectively, 90 kilo ohms and 10 kilo ohms respectively, and the supply voltage VCC is equal to 22.5 volts. Then the beta of the circuit of the transistor is given as 55. Now with the base side biasing R1 equal to 90 kilo ohms, R2 equal to 10 kilo ohms and the collector supply equal to 22.5 volts, we can get the Thevenin's equivalent V as R2 into 22.5, that is VCC, divided by R1 plus R2, that is 90 plus 10. So gives us 2.25 volts. This is the Thevenin's voltage. Similarly, the Thevenin's resistance RTH can be obtained as the parallel combination of 10 and 90 kilo ohms. So which gives us 9 kilo ohms. So with this, now we have this circuit, the Thevenin's equivalent on this side, and with this given by 2.25 volts, and this one equal to 9 kilo ohms, and this resistance given as 5.6 kilo ohms, and this voltage is equal to 22.5. And here we have a collector emitter resistance of 1 kilo ohm. Now using the first equation, so that is the equation on this side, with this voltage taken as about 0.65 volts and this is 1K, and this current, if this is the base current IB, so this is equal to IE, that is 1 plus beta times the IB. So the first equation is 2.25 is equal to 9 IB plus 0.65, 9 IB plus 0.65 volts plus 1 into 1 plus beta is 56 into 1 kilo ohm into IB. So from this we can obtain IB as about 24.8 microamperes. By solving this equation we can get IB as 24.8 microamperes. Now substituting for this IB in this loop, so wherein this loop is 22.5 volts is equal to 5.6 into IC plus VCE plus this is 1 kilo ohm into 56 into IB. So that is 56 into IB, and so given IB we can determine IC by multiplying it by 55, and what we get here is 1.36. We get IC equal to 1.36 milliamperes. That is 24.8 into 55. It gives us 1.36 milliamperes. That is IC. Now by substituting for IC and IB here, and from this equation we can determine VCE as, the collector to emitter voltage can be determined as 13.5 volts. Therefore, now the Q point is 13.5 volts and 1.36 milliamperes. So this is the Q point. So this is how, using the Thevenin's equivalent, we can analyze a given circuit and determine the Q point. And as I explained, the design problem is the inverse problem, wherein given the Q point, we can determine RC, RE and the Thevenin resistance. And when the unknowns are more than the number of equations which we have here, we have to choose some value, choose a convenient value for one of the variables and determine the rest of the variables. Now, as I stated in the earlier lecture, the cell bias circuit or emitter bias circuit helps us in improving the stability of the amplifier, biasing of the amplifier. Now, let us quantitatively see how the stability, how much is the stability of the circuit. Therefore, the question of quantitatively analyzing the stability is there. As I have mentioned, the stability is with the instability of a biasing circuit is due to several reasons. That means the collector current IC is a function of IC naught, that is the reverse saturation current when the emitter, when the base is open, the collector current when the base is open, and it is the reverse saturation, the collector current when the base to emitter bias is, junction is reverse biased. Then the instability can also be due to beta, as I have explained in the earlier class. That means IC is a function of IC naught, beta, and also base to emitter potential. And out of these, IC naught and VBE are an indirect effect of the temperature. As I mentioned earlier, IC naught gets doubled for every 10 degrees centigrade rise in the temperature. Hence, the IC naught really acts through the junction temperature or the transistor temperature. Similarly, the base to emitter potential also varies according to temperature, and as a result of which the collector current changes with temperature. Now, we can determine this delta, the stability in a quantitative manner like this. We can express delta IC as a partial dependence of del IC over IC naught multiplied by the change in IC naught that has taken place plus the partial change in IC due to the partial change in VBE multiplied by delta VBE, that is the change that has occurred in VBE due to some temperature variation, plus the change in the partial change that occurs in the collector current due to change in beta multiplied by the change in beta that has occurred because of changing the transistor from one transistor to another transistor, or it can also be due to a change in temperature, but the change in temperature causing a change in beta is very small. Hence, so this represents change in beta because of the changing in device. Now, having expressed the change in collector current as a function of the changes in these quantities like IC naught, VB and delta beta, we can mathematically express it in this form. Now, please note that the quantities dou IC by dou IC naught, dou IC by dou VB dou IC by dou beta, or a result, or can be determined given the circuit and the transistor characteristics. Now this parameter dou IC by dou IC naught is a stability parameter S due to the temperature variations, due to the IC naught variations, which are as a result of the temperature variations. Similarly, we can determine delta IC by delta VBE or dou IC by dou VBE as a stability factor S dash, and similarly we can determine the dou IC or represent dou IC by dou beta as the stability factor S double dash. And given the circuit and the particular transistor, if we know S, S dash and S double dash, we can determine the change in the collector current that takes place for given changes in IC naught, VB and delta beta by substituting for these parameters here and the respective quantities there. You can determine delta IC. Now, given a circuit, we can determine the stability factors S, S dash and S double dash. Of these, I will give an example of the stability factor S, and rest of the parameters S dash and S double dash also can be similarly obtained. Here I will discuss about S, and the rest of them can be obtained by yourselves using by going through any one of these textbooks. Now, as defined here, the stability factor due to IC naught can be given as S is equal to delta IC by delta IC naught. At any given IC, we can determine this S and given the circuit. Now let us consider the self-bias circuit, which we have discussed earlier, that is this kind of self-bias circuit. And in this circuit, let us see when how IC varies by changing IC naught. In the expressions which are given here, IC naught was neglected and we have obtained the Q point. Now to find the variation of IC due to IC naught, it is necessary to express the various quantities like IC and VCE in terms of IC naught. Hence, we have to use the accurate expressions here in this analysis. The accurate expression for the analysis can be obtained by substituting for IC as a function of IC naught. And we know that the approximate expression for IC is beta IB, and the accurate expression includes the term using IC naught, that is 1 plus beta into IC naught also. So this is the accurate expression for IC, and IC is related to IC naught in a given transistor. But in a given circuit, the circuit may not permit the IC to vary according to this relationship itself directly. In a fixed bias circuit, of course, IC is directly related in the circuit to 1 plus beta IC naught. Hence, if you determine dou IC by the stability factor S, S for fixed bias can be obtained as 1 plus beta, a fixed quantity, because dou IC by dou IC naught is equal to 1 plus beta. There is nothing in the circuit which prevents IC from being related to IC naught in this equation. Therefore, this equation holds good in the case of a fixed bias circuit. Hence, dou IC by dou IC naught gives you 1 plus beta, and that is the stability factor. And in the case of a self-bias circuit, the circuit doesn't permit the IC to rise according to this equation. And let us see how the stability factor can be analyzed given the self-bias circuit. Substituting this for this in the cell bias circuit, it can be shown that on the input side equation, VB is equal to the Thevenin's equivalent V Thevenin plus the Thevenin's equivalent R Thevenin plus RE into beta plus 1 by beta into IC naught minus R Thevenin plus RE into 1 plus beta by beta into IC. So please note that in the absence of IC naught, that means by neglecting IC naught, we get this equation VB equal to V Thevenin minus R Thevenin plus RE into 1 plus beta by beta whole into IC. Now, because of the accurate expression, usage of the accurate expression, we have this term coming into the picture. Similarly, the output side equation can be written like this, where we can use the term IC naught. The IC naught flows through RC also. Therefore, VCC is equal to RC into IC plus IC naught, IC itself plus VCE plus the voltage drop across RE. Now, for the input side, this expression is important for us. This is one expression and the other expression is this. So therefore, this is not useful for us for this analysis, therefore I am not bringing this equation into picture. So this is one equation and this is the second equation. We have to use these two equations. By using these two equations, we can determine delta IC by delta IC naught. Now from this equation, when VB is constant and naturally V Thevenin is constant, we can determine delta IC by delta IC naught. And by determining that, we can find S as delta IC by delta IC naught as equal to 1 plus beta multiplied by 1 plus R Thevenin by RE, so divided by 1 plus beta plus R Thevenin by RE. So this is the expression for the stability factor. Now, when RE is negligibly small or when RE is 0, please note that S is equal to 1 plus beta. And when RE is 0, the circuit becomes a fixed bias circuit, and the stability factor for a fixed bias circuit is 1 plus beta, as I have discussed earlier, as I showed earlier. And that is valid from this expression also, you can get the same thing. Now, when RE is very large compared to R Thevenin, then this is negligible and this is negligible, and the stability factor is equal to 1. Therefore, for a cell bias circuit, the stability varies from 1 to 1 plus beta. If RE is very large, the stability factor is close to 1, and if RE is very small, the stability factor is equal to 1 plus beta. RE is very large and very small means the in comparison with R Thevenin. It's because the R Thevenin on the input side, it is the R Thevenin and the RE which decides the operating point. I repeat, here given a fixed voltage here, R Thevenin and this feedback through RE, so which decides the stability. I repeat, if there is a tendency to increase in the collector current, and that collector current, increase in the collector current reflects in as an increase in the voltage across RE, and so this increase in the voltage RE causes this VBE to decrease. because this voltage is fixed, and if IB is fixed, this voltage is fixed, and when this rises, this has to decrease. And because of this reason, now when VB decreases, IC decreases. So if there is a tendency to increase IC due to IC naught, the circuit is such that it tries to reduce IC. Therefore, stability is improved. And naturally, this quantity depends on the value of RE. If the value of RE is large, if there is a slight change in IC naught, there would be a large change in VRE here, and that will cause this VBE to decrease, and thereby thereby IC. On the other hand, if this is 0, there is no change in this voltage when there is an increase in the collector current. Therefore, there is no feedback. Hence, RE, the value of RE plays an important role. And with increased RE, the stability goes down. So that's what this expression shows. Usually, circuits can be designed, or it is important that we maintain a value of S which is of the order of 5 to 10. Practically, 5 to 10 is good for normal applications. However, for high temperature applications, this S, the stability factor S, has to be maintained at a lower value than this. Similarly, we can have expressions for the stability, other stability factors, and the stability factor due to beta and the stability factor due to variations in the base tree emitted potential can be found in the literature, and the reader is advised to go through the literature. Now, there are other circuits which can be used to bias a transistor to make use of it work like an amplifier. There is a collector to base bias circuit. And this circuit uses the same output side circuit. So it also uses, at times it uses an emitter resistance, and at times it doesn't use an emitter resistance. Let us now take a case where it has no emitter resistance, and the biasing, that base current, is produced by a biasing circuit from the collector to base, through a biasing resistance from collector to the base. So this is the circuit. We can feed the signal here and take the output of signal from here, which will be discussed in subsequent classes. Now, as far as biasing is concerned, the base current is supplied through a resistance RB connected to the collector point. Therefore, it is known as a collector to base bias. Please note that in a fixed bias circuit, the biasing is provided from the supply VCC through a base resistance to the base. Here, it is provided from the collector. Now, what is the advantage you get by connecting this point to the collector rather than the supply? Please note that due to any one of these reasons, namely the change in IC naught or the change in VBE due to temperature variations and change in beta, if there is a tendency to increase or if there is an increase in the collector current, then what happens is the voltage drop across this resistance, this RC, increases. When this voltage drop across RC increases, the potential collector to ground potential decreases, because the collector to ground potential is equal to VC itself, that is VCC minus IC into RC. Hence, so this potential goes down. And when this potential goes down, the base current goes down. And when the base current goes down, the collector current goes down. Therefore, if due to some reason or any one of the reasons which have already been explained, the collector current increases, the base current decreases, and which in turn reduces the collector current. Therefore, the stability, bias stability is provided by the circuit through a collector to base bias. Now, on the input side equation can be written like this. This VCE is equal to the voltage drop across RB due to IB plus VBE. Therefore, this VCE is equal to IB into RB or RB into IB plus VBE. So, from this equation, the IB that flows in this circuit is equal to VCE. From equation, second equation, we can get this VCE minus VBE, which is of the order of 0.6 to 0.7 volts divided by RB. Therefore, if VCE falls due to an increase in IC according to this equation, now IB falls. With the falling VBE, naturally IB falls. IB decreases. When VC decreases, IB decreases. Hence, IC decreases. Now, this circuit, the quiescent point analysis of the circuit can be done using these two equations. Besides, we have to use the equation, as you know already, IC equal to beta IB. Similar to the self-bias circuit, the stability analysis of this circuit also can be carried out. But the self-bias circuit offers better stability than this circuit for the usually used values of the resistances. Now let me discuss about a condition known as thermal runaway, a situation known as thermal runaway. As I have already explained earlier, when temperature rises, when T rises, IC naught rises, and when IC naught rises, IC rises, collector current rises. And when IC rises, the power dissipation in the transistor rises, because power dissipation in the transistor is approximately equal to VC into IC itself, because VB into IB is negligibly small. So the power dissipation is approximately equal to VC into IC. When IC rises, the power dissipation may rise. And when the power dissipation rises in the junction, in the collector junction, then so this one also results in an increase in the temperature. And when temperature rises again, IC naught rises and IC rises, and when IC rises, there is a tendency to rise, the PD rises, the power dissipation rises, and as a result of which again temperature rises, and we may find that the transistor ultimately goes out of the active region and it may go into saturation region. And this condition is known as thermal runaway, and sometimes the transistor may get burnt. So this condition is known as thermal runaway. Now, there is a means by which this condition can be avoided. A circuit can be designed such that this condition can be avoided. Now, from the output circuit side, even in the fixed bias circuit, we know that even in the case of a fixed bias circuit, if this is VCC and this is RC and this is IC, Now VCE is equal to VCC minus RC into IC. Now once we have this kind of a circuit, once we have a collector resistance in the output side circuit, if collector current rises due to temperature rise or due to one of these reasons, if collector current rises, then I mentioned earlier that power dissipation may rise. But if you have this kind of a situation where RC is used, then when IC rises, VCE decreases. And when IC rises, if VCE decreases, then we can see that the power dissipation decreases. We can see that the power dissipation decreases. Depending on the particular VCE and IC, depending on the value of resistance RC, the rise in IC may be very large and the fall in VCE may be small, in which case due to a temperature rise PD may increase. But if the fall in VCE, the contribution due to fall in VCE is more than the contribution due to rise in IC in the power dissipation expression, because it's a product of these two, we can see that actually power dissipation goes down if IC rises. And when the power dissipation goes down when IC rises, we can see that the temperature rise can be reduced. Now how to take care of this problem? Now if you look at the power dissipation, constant power dissipation curves of a transistor, which is on the output side characteristics, when you operate the transistor at a particular VCE and IC, the product VCE into IC is the power dissipation. Therefore, the constant power dissipation plots are like this. This is maybe PD is equal to say 30 milliwatts, and say this is PD is equal to 20 milliwatts. Like this, we have different constant power dissipation plots. If ID is say 10 milliamperes, VC should be 2 volts, therefore IC into VC is equal to 20 milliwatts. So this is a say 20 milliwatts plot. For another IC, you need this VCE to get 20 milliwatts of power dissipation. Therefore, these are constant power dissipation plots. Now, if you bias the transistor such that the load line is at this point, load line is passing through this point, then when IC rises, please note that load line is given by this equation, VC is equal to VCC minus RCIC. It is an equation between VC and IC. It's a straight line equation with this point given by VCC and this point given by, that is when IC is equal to 0, VC is equal to VCC, this is VCC point, and this point is when VC is equal to 0, IC is equal to VCC by RC. This point is VCC by RC point on the current scale. Now, if IC rises, VC decreases according to this equation, and that equation is this straight line. Therefore, if IC rises, the Q point will shift to another point. Say this Q1, so Q point will shift to this point. When the Q point is shifted to this point, so what happens to the power dissipation? Well, it will fall in on another power dissipation plot curve, and this power dissipation curve is on the lower side. So this power dissipation curve is on the lower side of the 20 milliwatts curve. Just please note that the 20 milliwatts is just an example. Therefore, if IC rises, the power dissipation goes down. If IC falls, it will go to another Q point. For example, this point, then even then we are on the lower power dissipation side. Therefore, power dissipation goes down. So we can see that the power dissipation goes down if there is a rise in the collector current. By biasing the VCE on this side, how do we get that? Please note that when you bias it on this side, here for example, if you bias it on this side, now if the temperature rises, if the collector current rises, the Q point will move to this side. Now initially if this was the power dissipation curve, now the power dissipation curve will be this. Hence, there will be a rise in the power dissipation if the biasing is made such that VCE is on this side. So VCE has to be in this region. That means VCE has to be less than VCC by 2 for the Q point to rise, to remain on this side. So the selection of the Q point should be done such that, so this voltage VC is less than half of VCC. That means we want to see that this voltage drop is more than this voltage drop. Then we can ensure that the Q point is always either here or at the most here or on this side, this part of the curve, because of which when the temperature rises, VC decreases and the power dissipation curve, that the power dissipation goes down. I repeat, if it is biased such that VC is greater than this point, now the power dissipation increases as I showed at this point. So this way a Q point can be selected and selected such that the thermal runaway condition is avoided. So a Q point selection is important to this effect.